All right. So in this module, we will quickly review some basics about properties of matrices. In particular, we will concentrate on finding the eigenvalues and eigenvectors of a matrix. And along the way, we will show how this is related to many of the other things that we have been talking about in this course. We will try to keep this largely self-contained. This is a sort of a separate module from our course structure. So this is just to make you comfortable with and jog your memory about the basic facts about matrices. Okay. All right. So let us start with what an eigenvalue problem means. Eigenvalue problem in the case of matrices is simply the following. So you have a matrix A, okay, and it acts on some vector V, okay. Now, you can imagine for concreteness, this is a 2 by 2 or a 3 by 3 matrix, in which case this vector is either a one column 2 row matrix or a 1 column 3 row matrix. Of course, this matrix can act on this vector in various different ways, but there are certain special classes of vectors for associated with every matrix, such that A acting on that vector gives you something times the vector itself back. Okay, in general, it gives you some new vector, but certain special class of vectors obey this very nice property that a matrix times the vector is proportional to the vector itself. Okay, this is called the eigenvalue equation, as you know. Equation. Okay. So our goal is, given a matrix, what are the various lambdas? Given A, what are lambda and the vectors V? Okay. In general, if A is a 2 by 2 matrix, there is 2 possible eigenvalues and 2 possible eigenvectors. Now these eigenvalues and eigenvectors eigenvalues can be distinct, or 2 of those eigenvalues can be same. We will now concentrate on the case where the 2 eigenvalues are distinct. And to understand this, let us take a very simple but concrete example. Let us take some matrix which I will call H. Okay. The connection to physics is that H is usually reserved for what is called the Hamiltonian of the system. And H is a very simple matrix that has 2 entries, E sub G, 0, 0, and E sub E. Okay. I'll tell you later what the physical significance of this is and why I'm choosing these very curious symbols. But for now, we'll just treat this as a purely mathematical problem. Okay. Now, what are the eigenvalues of this matrix? This is very simple to understand. You solve the eigenvalues by solving what is called the characteristic equation for the system. The characteristic equation for the system is H minus lambda times I. Determinant of this guy is equal to 0. Okay. So for this particular matrix, this takes the form Eg minus lambda 0, 0, Ee minus lambda equals 0. And this, of course, gives you 2 values. Lambda is either Ee, we call lambda 1. So let's actually do it the other way around. Lambda 1 is Eg and lambda 2 is Ee. Okay, this is actually very simple to obtain. It is very simple to obtain because there are no non-diagonal elements in this matrix. Okay, this non-diagonal elements are 0. So you actually see that there is a connection between obtaining the eigenvalues and the matrix being diagonal. If the matrix is diagonal, obtaining the eigenvalues is very easy. If the matrix is diagonal, the eigenvalues are simply the ones that you see on the diagonal elements. So if I look at a matrix like this, I can easily see that the eigenvalues are basically Eg and Ee. All right. So what are the possible eigenvectors for this matrix? Well, I can go ahead and solve the eigenvector equation for each of these eigenvalues. For example, let us take the first eigenvalue, H, V1 is lambda 1, V1. The second equation obviously is H, V2 equals lambda 2, V2. Okay, so let's take the first equation. Let us assume that there is some vector V1, which is the eigenvector corresponding to the eigenvalue Eg. Let me take this vector to have some components A and B. I have to figure out what A and B are. So how do I do this? I'll simply plug in this onsorts. V1 is AB into the eigenvalue equation. So the eigenvalue equation is HV1 is lambda 1 V1, H is EG 0, 0 EE, acting on the vector AB equals lambda 1, which is EG, acting on AB. Okay. The left-hand side is a 2 by 2 matrix times a column vector. So the left-hand side is also a column vector with 2 entries. The right-hand side is also a column vector with 2 entries. So if 2 vectors are equal, then it means that each one of their corresponding components or entries are equal. So the left-hand side is basically AEG, and this is EG times A plus 0 times B. The first, second entry is 0 times A plus EE times B. So this is BEE equals AEG and BEG. Okay. So this tells me the first equation does not tell me anything. It simply says AEG equals AEG, which is obviously true. The second equation tells me BEE equals BEG. Okay. Now this equation is obviously untrue because this tells me that EE equals EG. But I have assumed that the eigenvalues are non-degenerate, which means eigenvalues are distinct. So I will start with the assumption that EG is not equal to EE, which means that the only way this equation can be true, only way in which I can make sense of this eigenvalue equation is if I choose B to be equal to 0. So what this is basically telling me is that for this particular eigenvalue EG, A is basically arbitrary because the first equation I get is AEG equals AEG, which is basically not an equation for A at all. So A can be anything, but B has to be equal to 0. So any vector of the form A comma 0 is an eigenvector of this equation, where A can be anything with eigenvalue EG. Of course, the simplest choice is A equal to 1. So we choose V1 to be 1, 0. Okay, this corresponds to the eigenvalue lambda 1 equal to EG. Similarly, using very similar arguments, you would be able to understand that the eigenvector corresponding to the other eigenvalue corresponds to the eigenvalue lambda 2 equals EE. Okay. So this has a very nice form. So if I'm given the matrix H, which is EG 0, 0, EE, my eigenvalues or eigenvectors are very straightforward to determine. My eigenvalues are basically the diagonal elements. Lambda 1, 2 is basically EG, comma EE, and V12 is basically, V1 is basically 1, 0, and V2 is basically 0, 1. All right. So what happens if I complicate this problem very slightly? So let me complicate this. Let me take this as 1 and this as 2. I will retain the same diagonal elements for H, but I'll now put in some non-diagonal entries as well. So this is EG. Let me put some alpha star, alpha, EE, where alpha is some complex number. I'm choosing a very particular non-diagonal entry. Why I want to choose alpha star and alpha and not two different numbers in general, I will talk about later. But this is as good as an example as any other. Yeah. So for this matrix, what are the eigenvalues and eigenvectors? First of all, now the non-diagonal elements are not 0. So we cannot simply read off the eigenvalues as EG and EE. So we have to solve the characteristic equation, which is EG minus lambda alpha star alpha. This is EE. EE minus lambda equal to 0. Yeah. So this gives me EG minus lambda times EE minus lambda minus this entry times this entry, which is alpha times alpha star, which is mod alpha square equal to 0. So this is a quadratic equation in lambda, which I can solve. So let me write down what the quadratic equation is. So this is lambda squared, and I'm going to get minus lambda times EE plus EG plus EG EE minus alpha square equal to 0, right? So if I solve this, I get two different eigenvalues, and I'll call these eigenvalues, instead of calling them lambda 1 and lambda 2, I'll call them lambda plus and lambda minus. Okay, lambda plus and lambda minus are, if you work this out, you can simply solve the quadratic equation using the roots as minus b plus minus square root of b square minus 4ac over 2a. And if you use that, you would get EG plus EE plus minus square root of EG, this is EE minus EG square plus 4 alpha. These are the two eigenvalues you will get for this particular matrix. Okay. All right. So what's happening to the eigenvalues? Initially, when I did not have these off diagonal elements in my matrix, my two eigenvalues were basically EG and EE. Okay. Now, one of the ways in which you can check if this makes sense is if you make alpha to be equal to 0. Okay, if alpha equals 0, then this last term goes away and your eigenvalue should be 1/2 EG plus EE plus minus EE minus EG. Okay, and you would get either EG or EE. So it will work out properly. All right. The plus one would give you, I think, EE, and the minus one would give you EG. So this notation simply means lambda plus corresponds to the eigenvalue EG plus EE plus square root of this, and lambda minus corresponds to the eigenvalue EG plus EE minus square root of this. Okay, so the limiting case does make sense. If alpha equal to 0, then I don't have any diagonal limits and I get the exact same eigenvalues as before. How about the eigen vectors? So what are the eigenvectors in this case? Well, the eigenvectors in this case are H V plus equals lambda plus V plus, and H V minus equals lambda minus V minus. This is one eigenvector corresponding to the lambda plus eigenvalue and one eigenvector corresponding to the lambda minus eigenvalue. Okay. So how do I solve these eigenvectors? These eigenvectors are obviously more complicated than the previous case. Excuse me. Now I can actually go ahead and solve it in the exact same fashion I solved the previous one. What will I do? I will simply write this eigenvector, for example, B plus, as some A plus and B plus, and I had to find out what A plus and B plus are. Now when I write this V plus as A plus and B plus, this is one mathematical subtlety which you can ignore for this course, but I would still want you to understand. Is the following. So I can write this as A plus times 1, 0 plus B plus times 0, 1. Okay, so what I'm basically doing is the following. I'm writing the new eigenvector as a linear combination of the old eigenvectors. The old eigenvectors are the eigenvectors of the previous matrix. Of course, this actually is a statement about a beautiful subject called linear vector spaces, which we will not go into in this course. But notice that the new eigenvectors can be written as a linear sum of the old eigenvectors. And this is basically the claim that the eigenvectors 1, 0 and 0, 1 form a complete basis. Just like I, J, K form the unit vectors in ordinary three-dimensional Euclidean space. Anyway, so coming back to this problem, I will again solve for the eigenvectors using the exact same criteria as before. So EG alpha star, alpha EE, the matrix acting on the eigenvector A plus B plus equals lambda plus A plus B plus. Okay. So this gives you two equations. What are the equations? EG times A plus alpha star times B plus equals lambda plus A plus, and alpha A plus EE B plus equals lambda plus B plus. These are two equations for two unknowns, A plus and B plus, and you can go ahead and solve this simultaneous equations. And I will not solve it because it is just algebraically more complicated, but of course you can go ahead and solve these equations, and you can go ahead and write down what the eigenvectors are. Okay, you know what B plus equals A plus B plus is. Okay, so to give you one of the answers, A plus square, mod A plus square would be alpha square minus, I think, lambda plus minus EE whole square divided by lambda plus minus EG whole square minus. Okay, you can go ahead and verify if this is true, if this is what you also get. Okay, now you can go ahead and normalize the vector. How do I normalize the vector? Suppose if you have some vector v equals a and b, normalization simply means the dot product of v with itself is equal to 1. So that means v transpose v, which is equal to ab times ab, is equal to 1. You require this definition, okay? Demand that this vector be normalized. So this basically tells you that a square plus b square equals 1. Of course, if a and b are complex, then your equation should be v dagger v equal to 1, and this would give you mod a square plus mod b square equal to 1. So the advantage of using normalized vectors is manifold. One of the things is that once you know one of the components, you know what the other component is up to a phase. Okay, so I can simply calculate what b square is, because b square is basically 1 minus modulus a square. So you can use this normalizing the vector notation to calculate what b plus is for this guy. Okay, once you know what a plus is. Okay. So this is a very basic 10-minute review of how to calculate the eigenvectors and eigenvalues of very simple 2x2 matrices. But since we are doing a physics course, I should also tell you something about the choice of this matrix. This H, if I choose it this way, EG00 EE, is what is called, I can interpret this as the Hamiltonian of a system. Now we will, next lecture, we will try to understand what different operators are. So different operators give you certain physical quantities called observables in quantum mechanics. And the Hamiltonian measures the energy of the system. So this is an example of a system that has two states, a ground state with energy Eg and an excited state with energy Ee. So the fact that there is no elements in the off diagonal entries means that this is a non-interacting system. Okay, so for example, you can think of an atom with two energy levels. Okay, the lower energy level and upper energy level. Suppose if this atom interacts with something from the outside, like an external electromagnetic field, then these external electromagnetic fields can cause transitions between these two states. So we can make the electron from the ground state go to the excited state, or you can make the electron from the excited state come down to the ground state. Okay, so once you turn on this interaction, the Hamiltonian takes this particular form, something like this: Eg alpha star alpha Ee. Okay, now why is this alpha star and this alpha? Why cannot be this some complex number alpha and this some complex number beta? The answer has to do with the fact that Hamiltonian has to be a Hermitian matrix. Why? We will understand as we learn more quantum mechanics. Okay. So what is happening to the energy eigenvalues? Well, previously I had only two energy eigenvalues, one corresponding an energy corresponding to the ground state, which is EE, and one corresponding to the excited state, which is EE. But once I turn on this interaction, then this energy eigenvalues basically split into lambda plus and lambda minus, one which is greater than EG plus EE and one which is less than EG plus EE. So suppose if I want to show this graphically, what the lambda plus minus are, excuse me. So suppose if this is my zero, let us say, okay. So it will go like this and like this, okay. Of course, this is not completely symmetric. It is actually completely symmetric. These are my energy eigenvalues, lambda plus minus, okay. And this is a function of the interaction strength modulus alpha square, okay. So the top one, the excited energy state, actually becomes a new energy state whose energy is equal to the value EE plus EG plus square root of this guy, okay, EE minus EG whole square plus alpha square, and the bottom state is EG plus EE minus square root of EE minus EG square plus 4 alpha square. So one of them is greater and the other is smaller. Usually the ground state has the lowest energy, so the ground state corresponds to this lower graph and the excited state corresponds to this particular top graph. Okay, this is how it grows with alpha square. So this is typically what happens when you turn on interactions in quantum mechanics. What happens is sometimes we can have cases where you have two non-degenerate levels and both of them get shifted. Non-degenerate means the two eigenvalues are not equal. You can also have very curious cases in quantum mechanics when two levels have the exact same energy, and when you turn on some external external electromagnetic fields or some external disturbance, these two levels can then split into two. Okay, so we will not worry about such very peculiar cases. If you chance to take an advanced course on quantum mechanics, you will study all about these things. Okay, so the goal of this module was to basically familiarize yourself, in case you have forgotten, about how to diagonalize 2 by 2 matrices. Now, when I say diagonalize, I simply mean that finding the eigenvectors and eigenvalues is tantamount to diagonalizing a matrix. Okay, so what does it mean? So suppose if you have the two eigenvalues, so suppose if you have some matrix that has a set of eigenvalues and eigenvectors, and you have and you have figured out what these eigenvalues and eigenvectors are, they are lambda i's and vi's, then you can form a new matrix out of these vi's such that this new matrix, suppose if we have, let us say, two eigenvectors, v1 and v2, I can form a matrix V, which is basically v1 and v2 arranged this way. Okay, so let us say my eigenvectors are AB and CD. Okay, so I will form a new matrix out of them, which is equal to AB and CD. Okay, assuming that these are all complex valued matrices, you can show that B dagger HV is a diagonal matrix. Okay, so the act of finding the eigenvectors of a matrix is equivalent to diagonalizing a matrix. So if you have a matrix with non-diagonal entries, then you can form a new matrix with diagonal entries by multiplying the eigenvector matrix P that you found using this prescription dagger times the matrix times the eigenvalue eigenvector matrix again. Okay. So why is this a diagonal matrix? I leave it to you to understand. So simply take this 2, assume that A, B and C, D are eigenvectors that follow the eigenvalue equations with eigenvalues lambda 1 and lambda 2, and work out this V dagger HV combination, see what you get. You will get something that has only diagonal elements. Okay, that is left as an exercise to you. So the statement of diagonalizing a matrix and finding the eigenvectors of a matrix are equivalent statements. So if I hopefully this sort of jogs your memory and you have familiarized yourselves with eigenvectors and eigenvalues again. If not, please take a couple of examples and work them out, and I'm sure that you'll be able to understand all these concepts in no time. Okay, so for now, we will stop here.